I'm going to use the fact that if I'm asked to do d du of the natural log of u, then this is going to be 1 over u and then u prime. And I'm going to couple that with this other one, that if I have d theta of the tangent of theta, then this is going to be the secant squared of theta times theta prime. So I'm going to use those two combined. And the first part is I need to do the derivative of the natural log. So the derivative of the natural log, so y prime, or dy dx, is equal to 1 over the u. In this case, u happens to be the tangent of 4x squared. Now I need to multiply it by the derivative of the tangent 4x squared, because that's what u is. So here, u was the tangent of 4x squared. Now I need to find this u prime. My u prime is this part right here. So u prime is actually the secant squared of the angle times the derivative of the angle. So the derivative of tangent to the 4x squared is going to be the secant squared of my angle. But don't forget, I do need to do the derivative of my angle, and my angle is 4x squared, so I need to multiply by the derivative of 4x squared, which is 8x. So my answer is 8x, the secant squared of 4x squared, all over the tangent of 4x squared. Now, if you decided that you would like to clean this up with the trig functions that we know, then doing the cleanup, I know the secant squared of the angle is 1 over the cosine squared of the angle. And if I have 1 over the tangent of the angle, then this is the same thing as 1 over the sine of the angle divided by the cosine of the angle, which is just the cosine of the angle divided by the sine of the angle. So knowing all of this, then this is going to be equal to 8x, the cosine of 4x squared, over the cosine squared 4x squared, the sine of 4x squared. So my final answer, if I decide to clean it up, is 8x divided by the cosine of 4x squared, the sine of 4x squared. So looking back, this one is a perfectly good answer. This one is a perfectly good answer as well. They are equivalent. Is there any questions on those? Any questions at all? Okay. What we're going to be doing today is we're going to be doing something called U-Substitution. And U-Substitution is a time in your life where you get to say F-U a lot. You get to say F-U all the time. F-U, you. So you got to F-U, you, and the F-U, you. What we're going to be doing is U-Substitution. And you notice when I did the derivative d du of the natural log of u, then this was 1 over u prime. And I did that because there are times in which I'm doing the natural log of u and I'm not doing the natural log of x. It might be the natural log of cosine x. And the reason I'm introducing the derivatives first is because we're going to be undoing it. So if I have the derivative d du of the natural log of actually I'll just do d dx. So let me erase this d dx of the natural log of the cosine of x. Using this rule, then this is going to equal to 1 over, and I have the cosine, so 1 over the cosine of x. And then the derivative of the cosine is negative sine x. So I end up with negative sine x over cosine x. And if I'm really feeling fancy, I can write this as negative tangent of x, or negative cotangent of x, excuse me. Negative cotangent of x. No, negative sine over cosine, negative tangent x. So now if I'm asked to integrate the negative tangent of x dx, and I look at all of my rules, so I'm going to go and look at all of my derivatives. I'm going to rewrite the sine over cosine as the integral of 1 over the cosine of x. And then multiplied by, I'm going to pull that negative back in, negative sine x dx. Now, if you remember from my integral tables, I don't have the integral, I don't have tangent x. Or derivatives. I don't have the derivative of just the tangent x. When I did the derivatives, I didn't find any that's just the tangent of x. So it looks like 1 over. So if I see 1 over, every time I see 1 over, I think, man, I think that might be the natural log. That's what I think. So I'm going to let u equal 1 over the cosine, or excuse me, I'm going to let u equal the cosine of x. So that means I have a replacement. This becomes u. But now I have a u here, and I have an x dx. So I see sine x dx. So if I do the derivative of u, I'm going to get the cosine, the derivative of cosine, which is negative sine x dx. So now I have a replacement of this entire thing with du. So now that I have a replacement for the cosine x, I'm using the variable u instead of x, and I have the dx is what I'm really trying to do is I'm trying to get the dx into be in terms of du. So what I chose for u is going to hopefully, if I choose right, is going to give me a quick replacement for the other part where I see x. So when I do the derivative of cosine x, I get negative sine x dx. And so I have a replacement for both of them. So this is going to be equal to the integral of 1 over u and then du. Does that answer your question? Okay. And then just finishing this up again, is I'm going to get the natural log of the absolute value of u plus c. And the way that I chose u was I chose u to be cosine, so it's the absolute value of the cosine of x plus c, and so that's my last step to do. So what you choose for u, if you can't get a replacement for the dx part, if you can't write everything in terms of u, then you may not have chose the best u. So you may have to do a little bit of manipulation, but if you have to do a lot of manipulation, you probably didn't choose the best u for U-substitution. And if you remember, when you were in pre-calculus 2, when you were doing identities, whether that was a year ago or last year or however you did trig, that when you first learned trig identities, they were difficult because you had to learn the best way to get from point A to point B, how to get from the left side to the right or the right side to the left. And you know that when you started those, that the first couple of times you did it, it was not easy and it was not convenient necessarily on the ones that you chose. This is going to be something similar with U-substitution. Sometimes you're going to choose really well right out of the gate, and then sometimes you're not going to choose as well. As I was just watching Raiders of the Lost Ark the other day, and it was, you have chosen poorly, or you have chosen wisely. So until you get a good idea for U-substitution, there's going to be times where you can think of that night saying you have chosen poorly. So that's okay. U-substitution. That's what basically that we are doing today. So first thing that when you're doing U-substitution is figure out which one would be the best U. Once you figure out which one is going to be the best U, then you're going to substitute U into that function, and you're going to say U equals that g of x function. And then du is going to be hopefully going to be equal to what I chose U to be in terms of x, dx. So hopefully when you do your first choosing that it will fall out easily. It doesn't always though. Sometimes they don't fall out very nicely, and that means that you haven't chosen the best, or you may have to do a little bit of manipulation algebraically. So once I've done that, if it is a indefinite integral, then I just put the plus c. If I have a definite integral, then I have to change my limits of integration as well. So we're going to do an example again where I have it with an indefinite, so I'm just going to put the plus c. And then I'm going to do it with a definite, in which I'm going to change my integrals, and I'm not going to back substitute. Okay, does anyone need me to wait while you have the opportunity to write any of this down? Are we okay? Or can I keep moving? Are you still writing? Okay, I'm not getting any responses that you need me to stay, so I'm going to keep moving on. So when we're doing definite integrals, then what we want to do is we want to change these limits of integration so that we don't have to back substitute the u, what I decided u to be. So I'm going to do one of these with the definite integral, which I don't have any of those. Which one of these would you like me to do?
B.
B? Okay. So with B, I need to decide which one is the best U. Now I'm gonna show you when we're doing U substitution when you don't choose wisely. So if I think this one is U, I'm going to come over here and I'm going to say let U equal 6x plus 1. That means du is equal to 6 du. So I've got a replacement for this, but you notice I don't have a replacement for that. So even though I let u equal 6x plus 1, that is not a good choice. Not at all. That is not a good choice. Because I should be able to quickly have a replacement where it is, oh look, I think one fits the other. So I know that on B that wasn't a good choice. So then if that's not a good choice, what if I did this and I said, okay, what if I said let u equal the square root of 3x squared plus x? This is equal to 3x squared plus x raised to the 1/2. Now when I do du is equal to, and I have to use the chain rule, so it's going to be 1/2. Okay, constants are not a big deal. But then I get 3x squared plus 1 raised to the negative 1/2. And then I have to still do the inside. And that's going to give me 6x plus 1 dx. Now I take a look at that and I think, wait a minute, this is making it way uglier than what I start out with. So my u is not going to be the square root. But what I do see is I see this, which matches this. So instead of u being the square root of, what I'm going to do is I'm going to let u equal the 3x squared plus x. That's what I'm going to let u equal. So if I let u equal that, then when I do du is going to give me 6x plus 1 multiplied by dx. So this piece and the dx gets replaced with du, and this piece gets replaced with u. So what I have is the integral from the square root of u du. And this is a lot easier to deal with because I can write this as the integral u raised to the 1/2 du. And then to undo the integration, I'm just going to add 1 power here and then divide by that number. So this is going to be equal to u raised to the 3/2 divided by 3/2, in other words, multiply by 2/3, plus c. And then all I have to do is remind myself I need to put u back. So when I put u back, I get 2/3. U was 3x squared plus x, now raised to the 3/2 plus c. And I'm going to stop. I'm going to ask, what kind of questions do you have for me? What kind of questions do you have for me?
So to do the reverse of the derivative, you have to add 1 to the power and divide by that new power.
Yep. So when we are integrating, we are undoing the derivative. And when we do the derivative, we subtract a power and multiply by that power. So we have to undo that. So we add a power and then divide by, instead of multiply, by what that power should have been. Yes. What other kind of questions do you have for me? All right, I'm going to do C, and then I'm going to leave A and B for you to do. So if there's no questions on B, I am going to erase what I have. Oh, so the question somebody had is, where do I post them? Let me show you where I post them. So it'll take a minute just to come out of here again. We're going to do I'm going to do C to show you what do you do when you have to adjust for a constant that isn't there when I do the derivative. So let me erase this. And the reason I don't do the undo or the delete is because when I undo or delete, it takes it off the video. So just a little quirk. All right, so I'm taking a look at C. And what I know when I do the derivative d du of e to the u, then this is going to be equal to e to the u prime. So if I see e to some power, then my first initial reaction is to make sure I'm recording. Make sure that this part is the part that I'm going to replace with u. Whenever I see e to a power, I think that power probably is my u. So I'm going to come over here and I'm going to say, let u equal x squared. If I let u equals x squared, then du is going to give me 2x dx. Now as I go back and look at what I have the x and I have the dx. What's missing is the 2. And I need a direct substitution. So what I'm going to do is I'm going to divide both sides by 2 here. So I get 1/2 du is equal to x dx. Now I've got a replacement for my x and my dx. This becomes a du. And this x squared was u. So then this is equal to the integral of, don't forget the 1/2 e raised to the u, and then du. So then this is equal to, I'm just going to bring the 1/2 out front, e to the u du. And we like e to the u du because we know that e to the u du all day long, if I'm asked to integrate dx of e to the x, this equals e to the x all day long. We love e to the x. So then this must equal to 1/2 e to the u plus c. And then my last step, of course, is to go and replace u. So this is going to be equal to 1/2 e to the x squared plus c. What kind of questions do you have for me? Again, you can unmute yourself, you can raise your hand, you can post it in the chat window.
Can you show why having u equals e to the x to the 2 wouldn't be a good idea?
Having u be e to the x squared?
Yeah.
Okay.
Why the u
Okay.
x squared instead of the entire piece?
Okay. So if I said, I'm going to go down here and I'm going to do this in yellow. Hopefully you all can see. Let u equal e to the x squared, right? Is that what you're asking me? Okay. So if I let u equal e to the x squared, then du is going to equal, well, then I'm going to have the derivative of e to the x is going to be e to the x squared, and then multiplied by that derivative, which is 2x dx. And so I still have to do the division by 1/2, so division of du is equal to e to the x squared x dx. Then when I do this integral here, I'm going to have just 1/2 u du. So if I have 1/2 e of u du, then I can do the +1 and then divide by that, which is equal to 1/2 multiplied by u to the 2 divided by 2. And then I end up with 1/4 u, and don't forget the plus c, 1/4 u squared plus c. So if I do the back substitution, I'm going to get 1/4 e to the x squared plus c, which gives me 1/4 e, since I'm squaring this, it'll give me 2x squared, because it's a multiplier. So when I do the derivative, do I end up with the exact same thing? And the answer is no. I mean, my 1/4 will go away, but notice how this power does not give me this power up here. I'm glad you asked that question. Whenever you see e to the some power, almost always you're going to let u be that power. Almost always. Any other questions you have for me? That was a really good question. Okay, so if you don't have any more questions, I'm going to erase this part down here, and I'd like you to do, just erase and just taking a moment to erase. I'd like you all to do A and D, please. So A and D, please. I'm going to put this on pause and give you the opportunity to do A and D. If we let u equal 10x minus 3, then du is going to be 10x dx. Now, I have a replacement for this. This is going to be u. But I only see, and I don't even, why am I putting the x there? It's just 10x. I don't see a 10 there, so how do I adjust for the 10? Max, how do I adjust for that 10? So I don't see a 10 anywhere here. How do I adjust for that 10? Anyone? I lost Max. Madison, I think you're talking, but you're still on mute.
Yeah, I was about to say, it looks like Madison does. I don't know.
Okay, divide by 10. Yeah, divide by 10. And so when I do that replacement of dx, I'm going to replace dx with 1/10 du. So this is going to equal to, and I'm just going to pull that 1/10 out as a multiplier, 1/10 the integral of 1 over u du. And when I see that, what does that equal to all day long? The natural log of u plus c. Don't forget the absolute value. But what is u equal to?
10x minus 3.
And that's it. How are these two? Okay, a little shaky. It's okay if they're a little shaky.
So the antiderivative of 1 over u would be the natural log of u?
Yes, so when I see 1 over u du, then it always is the natural log of the absolute value of u. So when I see 1 over, and that's all I see is 1 over, my first initial instinct is at this point to say, oh, I think I have the natural log. That's what I think I have, and I think I have 1 over u. So then it leads me to, whenever I see that 1 over right here, 1 over some number, is I think I've got the natural log as the antiderivative, and I think it's 1 over u. So I think the denominator is my u, and then I look to see if that works out or not. That's where we are right now. Now when we start doing inverses and hyperbolics, not always, but right now that's how we look at it, is if I see 1 over, I think it's going to be the natural log. And then where the 10 came from, somebody asked me where did the 10 come from, is because when I'm doing the derivative of this, I do the derivative of 10x. When I'm doing dx of some constant times x, it's just going to be the constant. And so when I did the derivative of 10x, it's just going to be 10. But as I see where I start out over here, I'm just going to erase this. I'm writing all over this. I don't see a 10 anywhere. I see an dx. I see a 1 dx, but I don't see 10 as a multiplier. If there would have been a 10 right there, then I would have had a replacement of not having to divide both sides by 10. But right there it's a 1, so I need to adjust for it, so I had to divide both sides by 10, so that this 1 dx gets replaced with 1 over 10 du. So 1 dx gets replaced with 1 over 10 du, so that I can do this replacement here as u. Otherwise, without that divide by 10, I wouldn't have been able to do that substitution. What other kind of questions do you have for me? All right. So when I see you again tomorrow, we're going to just be doing a bunch more of these, because God only knows they're not delicious. I mean, these are the most delicious things you have ever seen in your entire life. And the reason that we are going to do a lot of these is because pretty much this entire quarter is going to be doing antiderivatives. So we need to get the U-substitution down, because when we do integration by parts, we're going to be doing a U and a V substitution, and it'll be the most delicious thing you have ever seen in your entire lives. You all have a great day. If you have questions, I will be available between 12:30 and 2 o'clock today, and I kind of figured out how to see when somebody's in the lobby waiting to come into office hour if I'm with a student, so I will let you in. If you need extra support one-on-one, just go ahead and shoot me an email, and we'll set up a time in which I can help you one-on-one. Otherwise, have a great day. Enjoy U-Substitution.